Hi all, I'm Sanchal Agrawal and my teammates are Nishat Kule and Guru Manikanta. We are working on a project, Learning Equality Curriculum Recommendation. This is a problem statement from one of the Kaggle competition. Here is the link to it from Kaggle. The problem statement is to enable students and educators to more readily access relevant educational content to support and supplement learning. Understanding the data, users can create their own channel, then build out a topic tree that represents a curricular taxonomy or other hierarchical structure, and finally organize the contents into these topics. Here is an example of a branch of a topic tree. Secondary education is a channel, and these are the topics and the content and the final content. The leaf topic of in this branch may be correlated with the content item, such as a video entitled with the polar coordinates. Dataset contains the following files: topic.csv, content.csv, correlation.csv. Topic.csv contains a row for each topic in the dataset. These topics are organized into channels, with which channel containing a single topic tree. Content.csv contains a row for each content items in the dataset. And correlation.csv contains the content items associated to topics in the training set. The dataset we just learned about has the data in 27 languages. So before getting into approach for designing the curriculum recommendation system, let us understand what is STS. STS is semantic textual similarity. It measures the meaning similarity of sentences. STS assesses the degree to which two sentences are semantically equivalent to each other. As mentioned earlier, the dataset content is in 27 different languages. We need STS to analyze the data and get recommendations. STS attempts to compare two texts and decide whether they are similar in meaning, that is, deals with determining how similar two pieces of text are. And the similarity score is given in the range of 0 to 5. 5 being completely equivalent and 0 being completely dissimilar. As we can see in the example here, the first sentence, a girl is styling her hair and a girl is brushing her hair. The similarity score is 2.5, whereas the second example, a group of men play saucer on the beach and a group of boys playing saucer on the beach. The similarity score is greater than the previous one, which is 3.6. As the two sentences are completely similar, just the difference is men and boys. So they seem to be more similar. For getting textual similarity, we can generate the features using various NLP techniques like n-gram overlap, edit distance, longest common prefix, suffix, or a substring, or using tree methods. After extracting the features, we can use any of the machine learning or the deep learning methods, algorithms like random forest or gradient boosting predictive ensemble methods for model development. This is definitely not an exhaustive list of all the possible algorithms that can be used, but these are the ones which are mostly used and having the high success rates. The most straightforward and effective method now is to use a powerful model like transformer to encode sentences and then give the similarity metric to compare the similarity score. Similarity scores are numeric measures to the basic questions on how close or related and how far or dissimilar the things are. There are different methods to compute similarity such as cosine similarity, Pearson correlation coefficient, and many more. For our project, we'll be using F2 score as our metric for similarity evaluation. Coming to the applications, STS has many applications, which include some like machine translation, summarization, question answering, etc. Here are the links to the resources that we will be using as we move towards a solution.
Now let's have a look at the data that we have for this problem statement. As Chanchal said, we had the data given to us in the three files: content, topics, and correlation. We then try to understand what each of these columns in this dataset stands for and which of them are more important to us. Since we are going to use the semantic textual similarity, the columns that have text in them and that elaborate the content will be our main focus here, like title and description. We started our explore data analysis by finding out if there are any missing or misplaced values in each data set. We can see many null values for description in both content and topic dataset. While there are many null values present for parent column as well in topic, it can be ignored for now, as our goal is to have recommendations for the topic instead of building a hierarchy. We can again see a lot of null values in the content dataset itself, but we can also ignore them for now, uh, as long as there is a title and description present. But this raises a question: what if both of these values are null? But we'll get to that later. We further studied the topic dataset, and we found that the channel value traces a tree that starts from a 1 0 level topic and further branches into lower level subtopics. Channel values are common for all these topics in the tree. You can see a representation of one of these channels here as a T diagram. There are no missing values present in correlation dataset, and so there is no further investigation is needed for correlation. Now coming to the main cursor that we had, what if both of the title and description values are missing? And indeed, there is a value in topic where both of these values are absent. We can't ignore or remove this topic as it has a lower level subtopic, but it also it also doesn't have any present content. Therefore, for such special cases, we will use topics from its channel hierarchy. For content, we have 6 such cases where both title and description are missing, but we can use the text feature of the content to make the recommendations there. After this, we analyzed each dataset individually to get basic insights from them. We started with the topic dataset. As you can see, the majority of the topics are distributed into the top 10 or so languages, with most in English. Here we can also see their category-wise distribution in the 3 fields: source, align, and supplemental. Now, for the content data, we can see 5 main types of content: video, document, HTML, exercise, and audio. As expected, most of the document data has some text associated with it, while other formats are not that consistent with text. Therefore, we are not going to consider text column as a main feature, but it will be considered for the special cases that we mentioned before. As the title and description will be our main features, we have tried to find the length of the string if we combine both of the features. For both topic and content dataset, most of the data has a low total number of words, and the count drops sharply after some value. Now, coming to the correlation table that gives the values of already existing content recommendations for the topic, same trend can also be seen here as the topics have single digit recommendations and the counts drop rapidly as the number of recommendations increases. We have recommendations for almost 28,000 topics with an average of 4.5 content per topic.
Given that we have the raw data, we would like to split it into train and validation because we don't have a separate test set. And it is supposed to be noted that we'll have to take extra care while splitting into train and validation because the problem statement mentions that the test set has about 10,000 topics that are not present in the training set. We would want to simulate the same environment for the train and validation split as well. So the topics present in validation are not seen in the train data. Once we have the train and test split, we would want to extract our features and then step into the actual problem of applying modeling. We can either follow one stage or 2-stage procedures. If we are going to go ahead with one stage, it is going to be very similar to any other predictive analytics problem. We train the model, perform any cross-validation as required, and do the evaluation. If you're going to use a 2-stage algorithm, in that stage, we would go ahead as usual with stage 1, where the stage 1 algorithm will will output some scores like a similarity or any other relevancy metrics. After stage one, we take those scores and any other input features and then train a stage two classifier. This classifier will then try to re-rank whatever scores are output by the stage one algorithm. Once again, we can follow the same procedure as we did before with cross-validation and evaluation. Irrespective of the kind of stage we're going ahead with, we can still perform some post-processing to identify the right threshold. After that is done, we would also once again want to train train the model on a full training set so that we're not missing out on any data. So I mentioned feature engineering, but I did not get into the details before. We can perform feature engineering by any of the various methods that are available outside, but these three, I believe, are most suited. We can perform vectorization through the most naive ways like account vectorizer or TF-IDF, or we can use contextual vectors represented by word-to-vec or doc-to-vec or the likes. Or we can even go ahead with an even more advanced mechanism where we're not just taking into account the context, but also the position where each word is used. This is basically the attention architecture that is used in the pre-trained large language transformer models. Once we have the features ready, we can then step into the training of the model. To train the model itself, we can use classification, question answering, or semantic textual similarity methods. If you want to use classification, the problem would be in a classification setup, each topic and each content are supposed to be given to a model to identify the right parameters for that particular pair. The same way, we'll have to define a huge set of pairs, which will be of the dimensions, the length of unique topics and the length of unique contents. That is going to be too huge, which is very time consuming and also very memory intensive. If we want to use a question answering method, we would like to use pre-trained LLMs because they have a lot of knowledge already and it becomes easier to fine tune our models. But the limitation is that all these models can only process a limited amount of text or the sequence length. What happens if our context is greater than that sequence length? That context could be greater than the sequence length because we are supposed to be defining the context ourselves explicitly. Because the problem that is given to us does not have a context given with each topic, but only the content and the topics. Since classification and question answering are out of the question, we would like to go ahead with semantic textual similarity. It does have a limitation where the sizes of matrices, the topic metrics, and the content metrics might be blown out of proportion, and we might run into out of memory issues. But the reason I didn't mention it as a limitation is because we can always do a batch processing. If we are to go ahead with semantic textual similarity, we can either use the ML methods like usual on the features generated, or we can use DL methods to both, to say deep learning methods to both generate the features and then train on them. So if we want to use the deep learning methods, we can use a pre-trained large language model to identify the embeddings first and then perform a fine tuning. So far, we've decided that we were going to use the one-stage training methodology because it is quick and fast. And we are going to use some pre-trained large language models once again because it is faster than generating features by ourselves and also more efficient, as shown by a lot of other researchers. And the inputs could be the title plus description. In case the title and description both are empty, we can use the other fields that are present in the given data set. And for the hyperparameters, we are going to go ahead with the original parameters for the concerned large language model or the pre-trained models. Even with this setup, we still have a few roadblocks. The first thing is with multiple languages that are present in this data set. There are about 27 unique languages, and the idea is for us to use one model because if we want to use multiple different models, it is going to be an overhead in terms of the usage in the final application. And like I mentioned before, large language models have a limit on the sequence lengths. So we would want to make sure that our input is not too lengthy so as to cross that limit. And we could also run into the out of vocab problems for the low resource languages. For example, we have Telugu in this data set, but there are not so many language models out there that can handle Telugu pretty well. Even if there are ones that can handle only Telugu or any other low resource language, it is a pretty good possibility that multilingual language models might not be able to deal with them that well. So how are we going to deal with these roadblocks? For one, to deal with the out of vocabulary issue, we are going to use the multilingual language models. Both of them that I mentioned here are multilingual. LABC, for example, can handle about 109 different languages, and Paraphrase model can also handle more than 40 or 50 different languages. I don't remember the exact number though. And like I mentioned before, the inputs might have all empty slots. In that case, we can utilize the topic tree hierarchy, where if for a given topic there is no data present, we can go a level up, take the data from the topic's parents or even grandparents. We would also like to introduce the contrastive learning objective to increase the distance between the negative pairs and decrease the distance between the positive pairs in terms of semantic similarity. And so, like I mentioned, the multilingual language models, LABC, for example, has 109 different languages that it can process, but still can run into the problem of out of vocab for low resource languages. In that case, we might want to consider a retraining of the tokenizer. And if time permits, we would also like to explore the two-stage training methodology that I mentioned before. So far, the pre-trained language models only have a humble performance of about 43 to 45% in terms of F2 mean F2 score. But I don't think that is pretty bad, considering that the leaderboard's highest score so far on this competition on Kaggle is about 75.